Hello, everyone. So we're going to start this last chapter, the last new chapter of this first semester here. It's actually a relatively short chapter, but you're going to see it's going to make stuff previously done, most specifically the alkyl halides chapter, that much more important because that's what we're going to be creating in this chapter is alkyl halides. So hopefully through all this practice, I've given you this sense that everything kind of ties together. So it's not like you can just forget the information that we learned from chapter 7 or chapter 8. Practicing all that's going to be really important. So if you find yourself having gone through this chapter a little quickly, because it is relatively short, make sure you're giving good practice to all the stuff that we've done previously. I did sort of design things such that we have a good bit of review time before the final exam. But you still want to get that practice in before even exam 4 because it's going to rely on some of that information, okay? But let's get started. So chapter 10 is all about radicals. First thing we're going to talk about is radical stability. So first of all, I guess, what the heck is a radical? We went over at very beginning of the semester the idea of a homolytic bond cleavage. Most bond cleavage that we've been talking about up until this point is heterolytic, meaning that when the bond breaks, both of those electrons are going to a new species. A homolytic cleavage, homo meaning like the same, right? Means that when that bond breaks, one electron, it breaks kind of, more or less breaks symmetrically. One electron is going to jump onto one of those species and the other electron onto the other one. Okay, so this would be in contrast again. Let's just hammer this home. If we had heterolytic cleavage, usually we would just draw that like this, one arrow, and that would represent both of those electrons jumping onto Y. So the result here would be X doesn't have any electrons and Y now has 2 extra, right? That would be the heterolytic cleavage. Homolytic cleavage is, again, that bond's breaking symmetrically. So one electron's jumping onto one species, the other one onto the other, and that creates what is known as a radical, okay? Different from a lone pair, right? A lone pair is 2 electrons that are sitting in this orbital. This is now something that's weird, an odd number of electrons, just 1 electron living in a given orbital. And what we're going to see is these radicals are very reactive. They don't really like having this unpaired electron kind of chilling all by itself, okay? Again, in contrast to the heterolytic cleavage, the other thing to point out here is the arrowheads are different. So in our heterolytic cleavage, we would use this 2-headed arrow that would show the motion of 2 electrons. For the homolytic cleavage, when you're showing the motion of 1 electron, you just have the fishhook arrow, right? So it's only got like a check mark sort of thing. Another thing that you'll notice, like pattern-wise, it's just a good idea to have a sight sort of information of this. These electrons will move kind of like in this bunny ears fashion as well, right? So we'll see this sort of like bunny ear thing going on as well. That's kind of a signature of these kind of mechanisms. Okay, now let's talk about the nature of a radical, right? So first of all, we know carbocations. So this is something, you have some methyl radical here, or sorry, methyl carbon ion here. That carbon has a positive charge, and what we've said about carbocations is it actually has an incomplete octet. It has an empty p orbital. Remember that empty p orbital led to this planar geometry, which was really important for stereoselectivity. Basically, if you had a nucleophile, that nucleophile could attack that carbocation from either the top or the bottom, and that would give you different stereoisomers, right? So the fact that that carbocation was flat had some stereochemical implications. Honestly, best case scenario, right? That meant that there wasn't any stereospecificity, which was really nice. The carbanion, on the other hand, has a non-symmetrical geometry. It's not, you're looking at it the same from both sides. It's not flat. It's actually a trigonal planar because that pair of electrons is actually occupying that p orbital. So that gives it that sp3 hybridized geometry. Okay. Yeah, so, and this of course would play the role, the carbanion would play the role of a nucleophile, as opposed to the carbocation, which would have been an electrophile. Okay, so now what about the geometry of these radicals? So there's kind of two competing ideas, although the outcome tends to be the same. So the whole idea, I guess, let's make it easy. Radicals also have this trigonal planar geometry. So just like a carbocation. And again, why that's such a big deal is because if you have a nucleophile, or in this case, it's not going to be a nucleophile, it's just going to be another radical. We'll see why in a second. It could attack from either the top. Oh, I guess I would do the fishhook, right? If I'm being good. Or the bottom. And thus you don't have any like weird stereochemistry to worry about, any inversions. You would always get a racemic mixture, okay? So moral of the story, radicals, best case scenario, you get a racemic mixture when you have these reactions. You don't have to worry about stereospecificity. In truth, there may be something a little bit more complicated going on, which is instead of it being purely trigonal planar, you do have this kind of like shallow pyramid, but it's rapidly inverting, meaning that the lone electron is jumping from, in this case, they're colored, the red orbital to the blue orbital, and that's causing a sort of inversion. The reason why the net effect of these are the same is because if it's inverting rapidly, then if you kind of had, you know, on average, it would look like a trigonal planar, right? So again, if it's rapidly going between the two, then you still, again, don't have any sort of stereospecificity. It's as likely for your radical to attack from the top, I guess, again, fishhook, or from the bottom. There's no sort of stereospecificity to worry about. All right, so then in terms of stability of these radicals, so the trend is very, very similar to a carbocation. It's actually identical to a carbocation. And that is that a methyl is the least stable and a tertiary is the most stable, right? So the more substitutions you have on that carbon, the more stable that radical is going to be, okay? Although it isn't the same thing as a carbocation in that it doesn't have that net positive charge, you still do have this incomplete octet that needs to be stabilized, right? So you have this hyperconjugation that stabilizes it more in the tertiary than in the methyl, okay? But again, that trend is just like what we saw for the carbocation stability. And actually, if you remember back to, gosh, I think chapter 6, when we were talking about predicting reaction enthalpies, we talked about bond dissociation energies. And this is how much energy you have to put in to break a bond. And it was actually specific to a homolytic cleavage of the bond, okay? So you can see this, we can do the, like kind of rank these bonds quantitatively using their bond dissociation energy. And the bottom line is the bonds that are harder to break, the ones that you have to put more energy into, they form less stable radicals, right? So a methyl carbon-hydrogen bond is much more difficult to break and thus forms a less stable radical than, for example, a tertiary. Allylic. So we talked about allylic carbocations, and just like that, an allylic radical is very stable. It's stabilized by the resonance delocalization of that pi bond. If we're going to show, so again, it's resonance stabilized. So there are these two resonance contributors that I can draw for that allylic radical. To convert between the two, right, we have our little mechanistic arrows, our electron pushing arrows we can show. Same thing here, but we're going to have to use the fishhook one. So let's see what that would look like. So this radical is going to come down. That's only this one fishhook arrow because it represents one electron moving. And if it's going to form this new double bond here, you need to have another electron, right? Covalent bonds are 2 electrons. So that other one comes from the homolytic cleavage of this pi bond here, right? So this represents the formation of that new pi bond, okay? Notice how, because this is a, you're using these fishhook arrows that only represent 1 electron each, you have to have 2 of them coming together to form a bond. Again, the bunny ears thing. All right, and then so then what about the other electron that used to be in this pi bond here? Well, that's what's going to become my free radical. So that's represented by, again, this is the homolytic cleavage of this bond represented by this arrow here and this arrow here. That is this pi bond homolytically cleaving. One electron is going to form a new pi bond in pink. The other electron is going to be that free radical. But yes, so this is why allylic radicals are more stable, because they can be resonance stabilized. Remember, resonance, it can kind of spread that unwanted charge, in this case it's the radical, across multiple carbons instead of it being isolated on one. And you can see the same thing with a benzylic as well. So just like you have a resonance stabilized allylic radical, and again, we can measure that using the bond dissociation energy. See, it's even easier to break than, say, a tertiary carbohydrogen bond. A benzylic radical is, again, that much more favorable because it can be resonance stabilized by all three of these pi bonds, not just one, okay? But yeah, so a benzylic radical would also be very stable. Notice that a benzylic radical would be on a carbon that's like one removed from the ring, right? I'm not talking about something like this, although that would be kind of allylic, but nonetheless, I'm talking about it's one removed from the ring to be benzylic. All right, and then the one thing to clear up, right, that we don't want to get confused is vinyl radicals versus allylic radicals. Remember, if I have, let's just take a simple alkene here. I have these allylic positions, which are one removed from the double bond. And then I have these vinylic positions, which are the sp2 hybridized carbons that are actually participating in that double bond. Allylic radicals, again, are quite stable, right? They're stabilized by that pi bond, which can move that radical around. Vinylic radicals, so if I had formed a radical with that blue carbon, those are very unstable. Notice that it's even less stable than a primary radical, okay? So although it's relatively easy to form a radical in the allylic position, we will not see radicals in the vinylic position, okay? And that's the difference is, again, just whether you're right on the double bond or one removed from the double bond. So if we're gonna like sort of compile a master cheat sheet here, this is what we see from increasing stability. Again, we have our super unfavorable vinylic and methyl radicals, all the way to our incredibly favorable, I guess we can lump tertiary in there too, tertiary allylic and benzylic radicals. Okay, so just keeping that in mind. And then one more thing to sort of note, what we're gonna see a lot are halogen radicals, and they would be even more stable over here. You can look up the bond dissociation energy for something like, for example, chlorine gas is going to be in the, I think it's like in the 250 kilojoules per mole range compared to what was it for the benzylic? Like 356. So this was 356. So these are even more stable. So your halogen radicals are by far the most stable. We're going to see them being the big players in these reactions.